Hello, friends. So, in the continuation of RC circuits series, today I discuss a few more aspects of this RC circuit. Before that, I would like to correct one thing that I think told in the previous video with some mistake. Maybe it some people has observed this thing, but okay, I'll correct that thing. So the point is that we have seen the circuit. We can have the excitation of type input voltage, input current, and whatever possibly means the nature of the signals can be there. I mean, they can be sinusoidal, they can be step, and whatever they can be, we have seen already in the previous video. But the discussion was there when we have input frequency infinite. Usually, what we say the capacitor is short circuited. So I have explained the reasons for short circuits, regions of cap to be shorted at higher frequency. One thing was very clear. We usually see that what is the magnitude of the impedance offered by cap at some frequency is what? It is omega c. And once this omega is very high, or I would like to say infinite, and what we can say is xc, the impedance offered by that particular capacitance is what I say zero. Okay, which is nothing but considering the cap as a short. This was the one reason I explained there. It can be considered as short. So other reason that I explained, this was a one reason. And other way of observing this, I explained that when we apply some sudden change across the capacitor. So here I did some mistake. Actually, I directly applied here some excitation. Let it was 2 volt initially. What it mean to say, if my this one plate is ground, if this is ground, then obviously what we can say, my upper plate is at 2 volt potential. This is a simple meaning. Okay, so if I'm suddenly applying a 5 volt signal here, what it meant to say at that particular instant, this voltage is varying from from 2 volt to 5 volt. As 2 volt was previously applied here, so I will say I told that del V is 3 volt. That is fine. Okay. So now the problem was actually the meaning there was not to apply this any particular excitation directly to the capacitor. When it happens, when we are applying some source and there is some sort of resistance in between, and then what we are applying, let's say now this particular case it was 2 volt, and here I applied some sudden voltage of let's say 5 volt. Then what will happen at this node? This node will not I would say it will not react fast in the sense because my signal is just applied at 0 means at t equal to 0. I applied a 5 volt, so there is a sudden application of voltage because let's see there is a no voltage before that. So 0 to 5 volt, so here is a infinite frequency, and this particular sense this capacitor will be shorted, and I already explained the reason why it is shorted. For the incremental voltage there is a no change across the capacitor. But the other thing is that if we directly apply voltage across the capacitor, it will be forced to change. Okay, so when we apply a voltage, when we apply a voltage directly across the cap, directly across the cap, it is forced to change the its change the its own value what is previously stored. Okay, change its own value. So it means when we are directly applying what I mistakenly told this thing, if it is a 2 volt and if we're directly applying a 5 volt here, then capacitor has to follow that 5 volt. Means it will leave its property of holding the current, holding the charge, because suddenly we are forcing two particular nodes. I will correct this thing again. What I mean to say, this is my capacitor. So let's say this node is at 2 volt and this is at ground. And suddenly if I apply by some wire, if I give some battery here, which is also one node is ground, so I can connect here. So if this is a 5 volt battery and I applied this battery suddenly at t equal to 0, then what will happen? Actually, what I am saying, I am forcing my capacitor with two nodes across the capacitor. I am forcing that to get this voltage. Okay. Even I can say if this voltage is ground, okay, no problem. So what will happen with the upper voltage? It has to follow what I am applying here. Overall, when we are making this connection, our KVL should be valid. It means to say what is the voltage input minus Vc equal to 0. Usually in any loop the KVL should be valid there, Vn equal to Vc. So it means it will follow that particular voltage. So when I directly applying any voltage across the capacitor voltage will also be 5 volt. So what it means, it upper plate will directly jump to, because lower plate is bound to ground, bound to 0 volt. So upper plate will directly bounce from 2 volt to 5 volt. So in this duration of del B of 3 volt, this capacitor will not hold its charge, will not follow this property, because again we are doing this. Okay, so we are doing this forcefully. Forcefully we are applying the voltage, then it has to change. And due to this sudden change in voltage, what will happen, how this means what particular phenomenon will happen when this capacitor will face this sudden voltage. Actually there will be a large current will flow, a large current will flow. Why? Because we know that what is del q? Del q is nothing but C into del V. And if we are suddenly making this change, del V of 3 volt, we are making a very rapid, what we can say, the charge will be suddenly. What I should say, I am applying, let's say this is my C, I am applying a 3 volt step, 3 volt impulsive, or impulsive voltage I am applying here, or not should say impulse. If I am just saying that I am applying a 3 volt step, better to say step, it is not an impulse. Okay, so I should say this is a 3 volt step suddenly I am applying to the capacitor, and this is my del q. Okay, 3 C ut sort of signal. So what is the current actually? What is the current? The amount of current that will flow equal to del q by del t. It is nothing but the current. So it is what, 3C dt by of ut. So it is nothing but impulse. So from the equation we can say a very large current will flow means an impulsive current will flow across the capacitor, flow across the cap. Okay, so the point here is, whatever I told, that suddenly if I changing, there this thing is only valid when there is some other circuitry, or whether it is R or not. If there is some other circuitry, and after that I am connecting my cap here. Okay, so it is some circuit, it may not be R, or it can be a combination of R also, it can be anything. So here I am applying some excitation E input, and there is a sudden change from one state to another, let's say 0 to 5 volt. Then this capacitor has to be shorted, because it will face, the system is providing me the very high frequency, then it will be shorted at high frequency. Simply means it will not show, or I will say it will not react to incremental voltage change in incremental voltage change in very small time. Okay, so if this voltage is changing slowly, let's say instead of this, if this is somehow this voltage, it is going from 0 to 5 volt, or I will say it is sinusoidal nature, then the capacitor will follow it. Okay, then my capacitor will follow it, and it will hold its property at every time. Okay, for smooth transition of input excitation, cap will follow it. Okay, cap will, I should write here, follow it. It means it will slowly increase, and at every instant when we will see, it will hold its own property, and we will say there is a no problem in that. Okay. Yes. So if we are forcefully applying something, then obviously the capacitor is forced to change its value across it. Then we cannot say anything. Okay. So now I will come back to that circuit and we will see the different ways of analysis with the different inputs. So we have seen what is capacitor is doing with the different frequencies. Let's see some more things on the capacitors. Okay. So I will say here more discussion on cap. Before going directly to the capacitor circuit analysis, I will go with the more things here. Okay. So what I told, if my this cap is here, let's say I am taking. So let it is has the charge of 2 volt initially, or I say this cap value is suppose 1 farad. So I can say it is charged to 2 coulomb. Okay. The other cap which is charged to 3 volt, it is also 1 farad, or I will say it is a 3 coulomb. Charge is stored across it. Now what I'm doing, if I'm suddenly making the connection, or what other thing I'm doing, one thing is that if I'm making a sudden connection, then what will happen? This is storing 2 coulomb and it is storing 3 coulomb, and suddenly we are connecting them. Then according to KVL, this voltage should be equal. Just at that instant only, when at t equal to 0, I am making the connection. Then what will happen? There is a sudden impulsive current will flow. Here this side is 3 volt and this side is 2 volt, and suddenly we are connecting them. The value is 1 farad. 1 farad. So what will there? They will share the charge, and suddenly an impulsive current will flow, and this voltage will be equal. Let's say this is the V. Okay. So what will be that V? So what I can say, what was the Q at the sum of the charge at time 0 negative, and what will be the sum of the charge at time 0 positive. Okay. So what was the sum of the charges? It was 2 coulomb plus 3 coulomb before we connected these two caps, and after that what will be there? There is a common voltage that I call the V. Okay, so this is V. So V into C1, sorry, V into C1 plus this same voltage into C1. This is the charge stored after the connection. So V is common because we are now connected. So C1 plus C2 is simply nothing but 2 farad. Okay, so what is this? 5 coulomb by 2 farad is nothing but sorry, V. Okay, so my V is 2.5 volt is going to be the sudden voltage across that. Okay, so these are few things that we should always keep in mind what is happening when they are connected suddenly. Okay, so it will 2.5 volt. So what will happen? Actually, this voltage will increase from it is 2 volt initially. So this voltage will increase from 2 to 2.5 volt. It will decrease from 3 to 2.5 volt. So what suddenly will happen if I talk about this is, let's say this is my cap 1. Both are equal of 1 farad, not a problem. But this is I will consider cap 2. Okay. So if I want to draw suddenly, if I want to see with the time what is happening with VC1. What was the BC1? BC1 previously was 2 volt. Let's say it was stored for a long time. And after that, instantly, it will change to 2.5 volt. Okay. And what will happen with the VC2 voltage? It was previously 3 volt, where it was charged previously. And what will happen at that particular instant when we connect it? It will also reach to 2.5 volt. In one curve, we can see it is happening somehow. One is coming from here, other is coming from here, and they are merging at this particular point. Okay, so this is a common voltage across both the caps. This is the nature that curve is following. Okay, we can say it was holding its charge, so this is on the t equal to 0 minus also. T is greater than 0 or also 0 minus, yeah. So it is on t 0 minus also. I'm showing the values. Okay. So what are the other possible combinations of the cap, let's say? Okay, so if my one cap has some charge of, let's say, 2 coulomb, this is a 1 farad, and other cap is charge 2. I am not forcing the other node to ground here, I'm just floating nodes. This is 3 coulomb and it is a 2 farad. Okay, now what I'm doing one thing, I'm making the stack. Okay, this is the second case I'm considering. So what doing here, so now I, let's say this is a C1, this is a C2. Now I'm making a stack of these two caps. This is my C1, this is my C2, and what I'm doing, I'm forcing this node to ground 0 volt, and I'm asking the value of this node voltage and value of this node voltage, that I'll call it V1 and V2. Okay, so what will happen with this? So one thing here is that the C2 has a 3 volt. Sorry, yeah, it is a 2 farad, 3 coulomb is stored. So what is the actually voltage across the capacitor? So VC2 will be what? This 3 coulomb by 2 farad is nothing but 1.5 volt across the capacitor. Okay. Now what is this? This is my VC1. What is the voltage across the capacitor? Voltage across the capacitor is again the charge by capacitor value is 2 volt and 1.5 volt. Okay, so what will happen here, we have to see one thing, this node, which both are nodes of this capacitor is floating. Okay, so here we will see both the nodes here are floating, and here also both the nodes are floating, no node is connected to ground. Okay, now what I'm doing, suddenly if I'm making this node to ground, then what will happen to this node? As soon as I am connecting this node to ground, this node will reach at some value by keeping the voltage across the capacitor constant. That I told you. What was this value? This is nothing but 1.5 volt. So it will try to keep this voltage at 1.5 only, and accordingly this V2 node will be set. Okay. So let us say here. Yeah. So what will be here? So wait. So as this node is set to ground, this node will directly jump to what I will say 1.5 volt, because it has to keep this difference of 1.5 voltage across it. Now suddenly what will happen to this node? This node is now 1.5. What will happen at this node? It will try to keep its own difference across it, which is nothing but 2 volt. So this node will suddenly jump to 1.5 and 2. It will jump to 3.5 volt. So what we can say, any particular connection when there is a isolated caps. So these are the isolated caps, isolated charged caps. Okay, and they are some connected caps, but upper node is floating. Connected caps. Now I say stacked caps, but other node is floating. Upper node is floating. Floating node V1. Okay. So this thing we can see, capacitor has this property, and when we are suddenly forcing particular node, the other node will adjust accordingly. Okay, so cap has this property, when we force, okay, when we force one node, other node adjust accordingly, because it holds, because it holds its charge for any incremental change, for incremental change of voltage across it. Okay, so my point here is that if I am making one node free, okay, previously what we have seen, one node was already fixed, this was the so 2 coulomb, because it was 1 farad. Okay, and so it ultimately means this was forced to ground, means this was ultimately to 2 volt, and now I suddenly force this node, and between these two nodes I connected the battery of 5 volt, and what is there, there is no scope for this cap to adjust its any node, because this is already forced. This node is already forced, and upper node is already now forcing, already forced to ground, and now I am upper node I am forcing to 5 volt. So the capacitor has no chance to follow its own property. It has to follow this 5 volt change, whatever the possibility we are applying externally, that del V it has to follow. But here what we are creating, here we are making it floating. Okay, so floating node has no means uh, forcing factor from the outside, that it should be adjusted according to that. So what it will do, both the caps will hold their properties of holding the charge initially, because this sudden application is what is the sudden application here? At t equal to 0, stacking is a sudden application of the voltage. Stacking is nothing but a, we are just forcing at t equal to 0, we are trying to make the change across the voltage across these two caps, because we are making the stack. What we have done, we forced this node to 0, and we are trying to, yeah, okay, what we have done at t equal to 0. So one can think, where is the like incremental voltage applied. So making this node to forcing this node to ground at t equal to instant, and making this sort of stack is nothing but applying some sort of incremental voltage at t equal to 0. Okay, this node is 0, so if this is also forced, then we can say the capacitor has to follow that particular voltage only. But as I'm keeping this floating, so they will adjust accordingly, and upper node voltage will be adjusted, so that they will have their own voltage values, like this is 1.5, this is the 2 volt we have seen here, and they will carry on with their own voltage, and after that this node will be 1.5, because this is ground, and this will be 3.5 voltage. So this was a concept I want to make with you people to clear. Okay, in the previous video, whatever the little mistake I have done, there was a point that when the resistor is there and some other circuit is there, then capacitor will react accordingly. When we are not directly applying any voltage across the capacitor, then it will react according to that particular excitation that we are applying. Okay. So these are few fundamentals of capacitor that we should keep in mind. In future, when we will see the question, we will see what other possible things can be discussed about the capacitor voltage and charges. Okay. Now come to the question. Okay. So now we'll come to the question. Okay. So we have seen that we have applied input, previously was sinusoidal input. We have applied Vm sin omega mt, and we have seen the output here. Now if I'm increasing frequency, so anyway, if I am directly applying some sort of signal, let's say second case, this was my first case, I already discussed. Now in this case, what I am doing, I am making a high frequency signal. Okay, high frequency signal, which is nothing but a sudden change. If I am applying a sudden change, let's say some sort of this signal, which is very famous question, we always seen this question. Okay, so if I am applying a step voltage, what will happen? I already told ways of analysis. So first I directly see that there is a cap. Okay, so what you see, we'll see the different time instants. Okay, what is happening at t equal to 0 negative, let's say. So any negative time instant where I'm with this is I'm applying at t equal to 0. Okay, 0 volt to 5 volt. So for time t equal to 0 negative means I'm assuming that my capacitor was already, the circuit was already in steady state. Okay, in this particular circuit was in steady state and no excitation was there. Circuit was in steady state. And one more thing that I will consider, that capacitor was uncharged. Capacitor was, okay. So simply means we see 0 negative as it was steady state. Simply I can consider that capacitor was already in particular state, and in a steady state simply it can be considered as the open, with the DC state simply. So it was 0 volt. Okay. So one thing that you know, that at t equal to 0 or 0 positive, or else 0 positive, I am applying a sudden input of the high frequency. Okay. So what will happen? The capacitor will be shorted. Now cap is shorted. If cap is shorted, then what will happen? Actually, suddenly, if we should see here, if this my cap is shorted, this is R. This I am applied here. Suddenly, the 5 volt, it was changing from 0 to 5 volt at t equal to 0. So now let's say it is sorted. Okay, so what is the output? Output at that particular instant is 0 volt. Okay, I got the point. So output at that t equal to 0 positive is constant, and what will happen? This is the time instant t equal to 0. This was my first time instant. This is my second time instant, and the third time instant I am considering that after a long time when t is much greater than 0 positive, or simply I should say t equal to infinite, or I should say steady state again is reached. Because we have applied excitation only at t equal to 0, so again it is a steady state after a long time, because my input is settled. Input was from 0 to 5. It took a transition from, means at t equal to 0 only, it took a transition from 0 to 5 volt, and after that it is a long time, it is a steady state for my input itself. Steady state, steady state input, which is nothing but 5 volt. Simply I can consider it as a DC volt. So what should I say? My cap should be open for the DC. So here I am directly considering two instants only. One is the t equal to 0 position, another is a t equal to very large greater than 0, means it is a simply infinite. So here it has been 5 volt and cap has been open. So this current is 0 volt, sorry 0 ampere. What should be the output voltage? As no current is flowing across the circuit, so this is also 0 ampere. So 0 ampere means 0 volt across the capacitor. This Vout should be 5 volt. And one thing that we can see, I got two values. Okay, I got two values. What I got? VC 0 positive is 0 volt only, and VC very large with infinite is 5 volt. And I also told you for the particular circuit there is a resistor is used in this particular structure. So the cap will follow its value, or it will hold its property at every instant. Okay, so it means it will follow some sort of charging mechanism, because we are going from 0 to 5 volt. Okay, so at max we are going from 0 to 5 volt. We are going from 0 to 5 volt, but I know that it is not going to make any sudden change across it, because already some resistive network is there also. So because of this resistive network, it is not going to follow like any hard and fast change across it. So it will follow some sort of change, slow change here. Let's say this particular, or whatever, this can be faster, slower. That will depend on what the state of the circuit is, means what is the time constant and all the things, we'll see it. Okay, so what nature, this is the nature of my curve. Nature of the output or cap voltage, because cap is the only at the output. So cap voltage itself is the output voltage. So this is the expected nature, I am not sure. So this is my expected nature. What I considered, initial there is no charge on the cap wheel, and here I applied the step of 5 volt. Simply I have seen this is my 0 volt, because it was at 0, and after that at some time I can say this is a 5 volt, and it will not follow the sudden change, because we already seen there is some resistive network, so it will follow some mechanism of charging sort of voltage, because it is not going to allow any sudden change across it. So it means it will follow some sort of this curve. So this is the nature of the curve. Oh, this is the nature of the output voltage. So we'll enter into the technicalities of this plot. What is the time constant or what is the slope? We'll enter into it slowly. So if I directly write the equation, then first I will write through the time domain. Then we'll do the means regress analysis of, means at every instant. We'll do the end intuitive analysis. Before that, I will write one equation. Okay, one time domain equation is that any transient voltage, which is I am to write weekly time constant term is there. So what is there? VCT, or simply V out T, is nothing but VC, what is it? VC 0 positive plus VC 0 positive minus VC infinite e to the power minus T by tau. Okay. So, okay, sorry, I think I missed one thing. This should be okay. So, first I'll write the transient equation, then we will see the intuition also. Okay. Yes. So, what is this? This is general transient equation. We write Vc of infinite. What is at infinite? Vc 0 positive minus Vc infinite e to the power minus t by tau. Okay, when we will put all this value, what is the Vc infinite? We have considered 5 volt from here, and what is the Vc 0 positive? That is 0 minus again what is Vc infinite? That is 5 volt e to the power minus t by tau. So what equation we will get? 1 minus e to the power minus t by tau. Okay, so this sort of nature of the curve we will get. Now I can put different time instant. What is happening at t equal to 0? T equal to 0 we can see from this equation what it is coming. It is coming as 0 volt. And what is happening at t equal to infinite? You can see Vc of infinite is 5 volt. So this is the equation that this equation is giving these voltages. So our assumption of considering this particular sort of nature is correct because it is following some exponential nature. Vct equal to 5, which is steady state value, minus e to the power minus t by tau. Okay, so what is the tau here? Tau is my time constant. Okay, so how will we calculate the time constant? Actually, this is a simple circuit. Only R and C is there. So this capacitor is charging through the resistor. Okay, so the simply time constant we will write there RC. Okay, or for any in general circuit, when we write the time domain, if there is any in general circuit, okay, if there is some sort of cap here, and if I am applying some excitation this side, and this is some resistive network, maybe I will say Rn is a resistive network. Okay, so then in that case, what will be there? Only one cap is there, so time constant will be R equivalent into C or R Thevenin into C. So we can draw the Thevenin equivalent for that particular circuit, and we can find what is the resistor, and only one capacitor is there. Then I can say R Thevenin times this resistance, or in general tau we can write if there are a lot of capacitor also there, then we can simply write R Thevenin and C equivalent or R equivalent C equivalent. Okay, that will be a tau. So here only one capacitor, one resistor. So I have written the tau equal to RC. So this is the exact equation. What we will get here is 5 1 minus e to the power minus t by RC. Okay, so now slowly we'll see if we are applying a different like we'll see what is happening exactly at different time instants. This is the zero, means zero is the initial value that I got, and after that the 5 volt is the final value that I got, and after that in between there's a nature of curve. I simply drawn some exponential sort of nature because my output has or capacitor voltage has to reach from 0 volt to 5 volt. Whatever the means nature it will follow, I am not worried about that. So we have verified this equation, this particular nature of the curve with the exponential equation that we have written the transient equation with this form. Okay, so we have verified this thing. Okay, so here we have seen the nature just by assumption, that not as an assumption. Initial value we have seen and final value we have seen, and after that we have just drawn a nature. And this particular equation follows both initial and final values in terms of time constant, where we have seen the exact nature, exponential nature it is following. Okay, so now we will see the what exact nature, what is coming as exponential nature, how it is coming, what is happening at other time instants. So if I go in a more depth, then what we can see, we can have the questions. Okay, then we can have the questions. What is happening at t equal to some t naught instant, which is greater than zero? What is happening at t equal to t1 instant, which is it is greater than sorry, I would say t1 is greater than t naught. So if I'm considering on time scale different time instants, this is my zero, some instant here, some instant here, and what is happening at every instant, and exactly what is the charging slope of the capacitor, charging current of capacitor. Okay, charging current of the capacitor, slope of capacitor voltage at different instants. So there are a lot of things we have to cover. So with these things will be clear by some intuitive analysis. Okay, some intuitive analysis that how it is happening actually. Then we can literally see for any random circuit what is happening at different time instants, and how we can see what is charging current, slope, and everything we will see related to this circuit. Hopefully this thing we will cover in the next video. So I covered, and I initially we have taken one confusion that I have done some mistake in the previous video. I removed from here, and then we will see what exactly happening when we are forcing the capacitor, and what happens when we are okay. So after forcing, we have seen this charge sharing also, and this after charge sharing, we have seen this example. In this, I particularly told, if I am forcing but one node is floating, then capacitors will automatically adjust themselves. So there is a no point of sudden change across the capacitor voltage. They will follow its property, their property. Okay. And after that, we have seen again what is happening at different time instants, and directly we went to this transient equation, and we have seen the exact nature of the plot of the output voltage or the capacitor voltage. So later we will see that how the current is flowing across the capacitor at different time instants, and from that particular can we draw this means plot, or can we write this voltage equation. It is going to be the most important thing, because this is the only way we usually deal the capacitor and the RC question. Usually RC question we deal in that way, because that is the only intuitive way. Otherwise, writing the equations and the frequency domain is a little easy. The intuition is something that is important from the placement viewpoint. Okay, so this is enough for this video. Thank you.